Imagine, for a moment, that the solid ground beneath our feet, the very earth we stand on, is just one layer of something. Well, much more complex. An unseen reality.
Yeah.
What if there's an entire universe, or maybe just a big part of one sort of dancing just beyond what we can see, influencing everything?
It's a really wild concept, isn't it?
Hmm.
Quite mind-bending.
Totally.
And today, we're diving deep into exactly that. We're looking at this fascinating paper, Earth's Dark Plasmasphere Structure and Dynamics by J. Alfred. It came out July 2025.
Right. And our mission for this deep dive is to unpack this really revolutionary idea. The idea that invisible dark matter structures aren't just out there in space, like in galaxy halos, but they actually interpenetrate our own Earth and the moon, too. So we'll explore what these dark Earths and dark moons, as they call them, might be made of.
Yeah, how they're structured.
Exactly how they're structured and what their dynamics, their movements might tell us about this hidden universe that's quite literally right here, under our feet.
It's kind of a shortcut, maybe, to understanding this surprising secret reality.
Totally.
And the basic idea, the core concept, is that these dark plasmaspheres are theorized to be made of something called dark non-thermal, or you could say cold complex or dusty plasma.
Okay.
And they're supposed to have properties really similar to plasma crystals and other plasma bodies we've actually seen in labs and, out in space.
So let's start with this invisible fabric itself. The paper mentions something called asymmetric dark matter around Earth. What's the premise there? How does that affect these plasmaspheres?
Okay, yeah, that's crucial. Asymmetric dark matter basically means there's practically no dark antimatter. So you don't get the big annihilations you might expect from some other dark matter ideas. Instead, it means dark matter particles just keep accumulating continuously.
Like a steady buildup.
Exactly, like a constant, gentle rain of dark matter just steadily adding up in these plasmaspheres.
Yeah. That sounds quite different from a lot of the dark matter models you hear about. So why plasma? Why would this dark matter end up in a plasma state? What are the conditions?
Well, it's not just one thing. It's more like a perfect storm of conditions described in the paper.
Okay.
First off, the dark electric charge. It's thought to be incredibly weak, like orders of magnitude weaker than our normal electric charge. Maybe only 100th or even 1,000,000th as strong.
Wow.
So it's just too weak to really pull particles together into stable atoms like hydrogen or helium.
Right. Not of a grip.
Exactly. Second, there are way more neutral or pseudo-neutral dark matter particles than charged ones. The estimate is about 5.5 times more neutrals.
Okay.
And this abundance of neutral particles acts like a buffer. It sort of dilutes the already weak electric forces even more, making it harder for charged particles to find each other and interact.
Like a cosmic cushion, sort of keeping things apart.
Yeah.
What else stops atoms from forming?
Third, the author's models suggest temperatures in these dark sectors might be higher than we'd typically assume.
Higher temperatures.
Yeah, giving particles extra energy, which also helps prevent them from settling down and binding into atoms. Then fourth, you get these really interesting thermodynamic effects. Big, heavy dark protons cool down much faster than the smaller, negatively charged dark electrons. This difference creates what's called non-thermal or cold plasma.
Okay.
Basically, particles have very different temperatures and speeds, which, again, makes it easier for them to stay separate and unbound.
That makes sense. If they're all moving differently, it's harder for them to sort of sync up and form an atom.
Precisely.
Okay.
Fifth, the overall density of dark matter in and around Earth is much, much lower than ordinary matter density.
Right.
So particles are much farther apart on average. This really favors long-range electrostatic interactions, the push and pull between charges, which is a key characteristic of plasma.
Okay.
And sixth, this one's a bit counterintuitive. While the dark matter particles generally move much slower than ordinary matter particles.
Yeah.
Paradoxically, this slowness, especially when density increases a bit, can actually help interactions happen and allow large structures to form. Fast particles might just zip past each other, but slow ones have more time to feel each other's influence.
Huh. That is a twist. And the final piece about viscosity.
Right. Even if the dark plasma isn't fully ionized, even if it's only partially ionized, there's this effect like viscosity. Electrostatic forces can indirectly tug on the neutral stuff.
How does that work?
The charged particles can sort of drag the neutral particles along with them, so even the neutrals start showing directional properties. They end up behaving a bit like dust in what scientists call complex or dusty plasma.
So even the neutral stuff, which you wouldn't think responds to electric fields, gets pulled into the dance.
Pretty much, yeah.
Okay, that brings us to these complex plasma features. What happens when electrons start sticking to these dust-like particles you mentioned?
Well, the paper describes how electrons would glom onto these bigger dust-like particles, building up negative charges.
Yeah.
But it's not static. This charge fluctuates. It changes, and that influences the plasma all around it. This whole dynamic process creates new ways for plasma waves to dampen, new kinds of waves altogether, and it leads to these incredibly intricate, self-organizing structures.
Wow.
It's like what we see in labs or in space with plasma clouds. It's just what plasma does when it has room. It built its own complex architecture.
Okay, so now we've got a sense of the unique material these things are made of. Let's meet the main characters, the dark Earths and dark moons. What are these things supposed to be?
So dark Earths are described as these near spheres of dark plasma. Their gravity is important, but those weak electromagnetic forces we talked about also play a big role in holding them together and shaping them.
Okay.
They're basically theorized as totally unique astrophysical objects, not like anything we usually think about.
And there's this comparison to brown dwarfs, but with limits. Can you clarify that?
Yeah, the analogy is that both are basically balls of plasma, not solid rock like our Earth. But that's where it stops. Unlike brown dwarfs, these dark Earths just don't have nearly enough mass or density to kickstart nuclear fusion, not for hydrogen, deuterium, or even lithium. So plasma, yes, but definitely not failed stars.
Got it. What about inside them? If it's plasma all the way through, what does that imply? Could there be, like, chemistry or even life?
Well, yeah, unlike our rocky planet, dark Earths are thought to be highly ionized through their entire volume, so forming stable atoms or molecules like we know them is much less likely.
Okay.
But, and this is where it gets really interesting, this high-energy dynamic plasma environment could allow for totally unique kinds of plasma chemistry.
Yeah.
And yeah, the paper even speculates about the possibility of biological processes within this plasma.
Plasma biology, wow.
It really pushes the boundaries of what we consider life and where it could pop up.
Seriously, thinking outside the box. So how do these things even form? Is it like how our Earth formed?
Not at all, apparently. The paper suggests a top-down origin for dark Earths. They form from these huge, collapsing cosmic dark matter halos. Yeah, which is the complete opposite of how ordinary planets like ours form, bottom up from bits of dust and rock clumping together.
Right.
The theory is actually that our ordinary Earth formed inside a pre-existing dark Earth, and it's still slowly accreting dark matter even now, which subtly, very subtly, nudges its orbit over millions of years.
So our planet is nested inside one and it's still interacting with it. Whoa.
That's the idea.
Okay, let's get into their structure and dynamics. How do they compare to something familiar like Earth's magnetosphere?
They're noted as being pretty similar, actually. In structure and dynamics, they have dark plasma sheaths, polarized regions, that kind of thing. But the scales is astonishing. The smallest theorized dark Earth is supposedly as big as Jupiter.
Jupiter size.
Yeah, and the lowest energy one. It's got a mean radius of about 70,000 kilometers.
Yeah.
You could fit over 1,000 ordinary Earths inside them.
Over 1,000 Earths inside one invisible sphere. That's just huge. Are they static, though, or are they active?
Oh, definitely not static. Think of them more like oceans of plasma. They're constantly being pulled and pushed by gravity from the Earth-Moon Sun system.
Right, tides.
Exactly. The paper describes them as constantly size-shifting and shape-shifting like a dancing candle flame. It depends on whether they're capturing or losing dark particles.
A dancing candle flame. That's a great image. Do they spin? Like Earth or the sun?
They do. Like the sun, they're rotating balls of plasma, and they likely experience differential rotation.
Cleaning.
The equator spins faster than the poles. This generates strong Coriolis forces, creates plasma vortexes. It leads to day and night cycles, but these would be much, much longer than our 24 hours, and probably variable too.
Huh. And luminosity. You said they're plasma. Do they glow even with dark light?
Well, yeah, being plasma, they should spontaneously emit dark photons, dark radiation.
Okay.
The paper suggests that if you could see dark radiation, their appearance would sort of oscillate in brightness. They'd fade in and out of view.
Like flickering.
Yeah, resulting in a shimmering or scintillating appearance. It depends on their internal plasma frequency compared to the dark light around them. It's a really bizarre, kind of captivating visual to imagine.
An invisible, shimmering world.
Okay, let's go inside the dark Earth now. How is the matter and charge spread out? We know the standard lambda CDM model for dark matter on huge scales, but how does this theory differ up close?
Right. The lambda-cold dark matter model works great for describing dark matter distribution across the cosmos, like how it clumps in galaxy centers.
Mm.
But when you zoom in to smaller scales, like within galaxies, observations show some differences. The density right at the very center of galaxies isn't always as high as the basic model predicts. Things seem a bit more complex near gravitational centers.
So the big picture is good, but the details closer to home are fuzzier, maybe more interesting. And this is where Manoj Kaplinghet's work comes in.
Exactly. Kaplan-Hatt's research indicated that if dark matter interacts with itself, self-interacting dark matter, its density tends to follow the density of ordinary matter much more closely on these smaller scales. It follows ordinary matter.
Yeah, which leads to this really powerful quote, essentially. While dark matter tells ordinary matter what to do at large scales, ordinary matter tells self-interacting dark matter what to do at small scales.
Wow.
And the huge implication there is that it suggests some kind of attractive force between dark matter and ordinary matter. The author even speculates this could be evidence for a new fifth force of nature.
A fifth force. That's massive. That could change everything. So what does this correlation mean for where the dark matter is inside our actual Earth?
Well, based on that idea, the paper predicts that most of the low-energy dark matter would be packed down below the Earth's crust. And because the core has such a small volume compared to the rest of the planet, the particle density there would be much, much higher.
So it mirrors normal matter.
Pretty much, yeah. It follows the stratification of ordinary matter, with the densest stuff sinking to the core. So you'd have a dark core inside our ordinary core.
A nested world indeed. Okay, now let's talk charge distribution and this Panacok-Rosselin electric field idea. Why is it so important that most dark matter particles are neutral?
It's absolutely key. Remember, maybe 85% of dark matter is thought to be neutral or pseudo-neutral particles.
Right, the opposite of our universe.
Exactly the reverse of ordinary matter, where charged particles dominate. This fact, combined with the really weak dark electric charge, means that separating positive and negative charges is much easier and more stable in these dark sectors.
Okay, so charges can separate and kind of stay separated. The paper calls the dark matter a colloidal fluid-like medium. Can you paint a clearer picture of that?
Sure. Imagine a really, really dilute soup, a vast soup,
Mm.
and suspended in that soup are the charged dark matter particles. But they're floating within this much larger medium of neutral particles, which can themselves be polarized.
Like tiny magnets.
Sort of, yeah. So it's like a suspension where the charged bits are distributed through and influenced by this bigger, invisible, electrically responsive neutral background.
And we have lab experiments that help us understand this.
We do. There's G. Tellis's experiment, for instance. It showed that in a gravitational field, heavy charged particles sink to the bottom, while lighter ones form a cloud above. It demonstrates this kind of plasma stratification.
Okay.
And then H. Thomas's plasma crystal experiments showed particles in the lab arranging themselves into layers, sometimes up to 18 distinct planes parallel to the electrodes, forming these stable, crystal-like patterns.
And these lab results connect directly to this Panacok-Rosselin field idea. How does that work normally?
Right. It's a well-known mechanism.
Yeah.
Basically, gravity pulls heavier positive ions down more strongly than lighter electrons. This separation creates weak electric fields. We see this happening in the sun's atmosphere, in the solar wind, in planetary ionospheres.
Right.
And the paper argues the same thing happens in Earth's dark plasmaspheres, but the effect is actually stronger, or at least more stable.
And why would these dark Panacok-Rosselin fields be more pronounced in dark Earths?
It comes back to those core properties. The weak, dark electric charge, the huge number of neutral particles acting as a buffer, the low density overall, and the different temperatures and sizes of the dark protons and electrons. All these things make it easier for charges to separate and then stay separated for a long, long time.
Which leads to this amazing idea of the capacitor Earth. How does our planet become a giant capacitor in this model?
It's a great analogy. So the heavy, cold, positively charged dark protons sink down towards Earth's core. They form a dense, positively charged plasma region below the crust. That's the E+ region.
Okay, the positive plate.
Exactly. Then the light, warm, negatively charged dark electrons hover much further out in a huge spherical shell or cloud around the dark Earth's atmosphere. That's the E region, the negative plate.
Got it.
And in between, you have the neutral particles. They're more massive and colder than the electrons, so they tend to dominate near the ordinary Earth's surface and also sink towards the core. They act like a neutral buffer, a dielectric, reducing the effect of the weak electric field between the E+ and E regions.
So you get this incredible layering. Positive core region, negative outer shell, and this neutral buffer zone in between, like a giant natural capacitor.
That's the picture, yeah. And this kind of stable charge separation is thought to be much more common and pronounced in dark Earths compared to regular stars or brown dwarfs, mainly because the forces holding things together are weaker and you have all those neutral particles.
Okay, let's zoom back out a bit. We've got dark Earth. What about dark moons? Same principle.
Pretty much the same idea. The moon also captures dark matter through gravity, so it forms its own dark moons with a similar structure. A positive core region, M+, a negative shell, M, and a neutral surface region, all co-rotating with the visible moon we see.
And if you have charges moving around in these things, you must get dark magnetic fields too. How are they generated?
Right. The sinking, cold, massive dark protons in the dark Earth's core would generate a weak electrical current. And that creates a weak dipole magnetic field, like a little bar magnet. Plus, you get weak vertical currents flowing between the positively charged core region and the negatively charged outer shell. These also generate weak global magnetic fields.
And then amplification.
Yeah, these initial weak fields are then likely amplified by a dynamo mechanism, similar to how Earth generates this magnetic field. It's driven by the rotation of the dark plasmasphere and also by convection, currents driven by heat differences.
Makes sense.
And once you have these magnetic field lines, charged particles spiral around them, forming what the paper calls dark Birkeland currents.
So very similar physics to our own magnetic field, just playing out in the dark sector. Now, this idea of plasma self-organizing, leading to nested shells and cells, how does plasma do that naturally?
Plasma is amazing at self-organizing. It can form structures called double layers. You can think of them like invisible insulating walls that the plasma builds itself.
Insulating walls?
Yeah, they electrically isolate different sections of the plasma based on their properties like density or temperature. They create distinct rooms or shells.
And if it's a sphere, these layers become spherical shells.
Exactly. In a spherical object like a dark Earth, these double layers would naturally form concentric spherical shells, one inside the other, separating regions of plasma with different densities, temperatures, frequencies, almost like layers of an onion or like those plasma crystals seen in labs.
Okay.
And what's really neat is that the magnetic field lines seem to provide the underlying structure, the skeleton, for these shells. And those dark Birkeland currents we mentioned, they flow along these magnetic field lines, accelerating charged particles as they go.
This sounds like it could apply to bigger things too. Does the paper connect this to, say, galaxies?
It absolutely does. It offers a potential alternative explanation for those faint concentric shells sometimes seen in elliptical galaxies, like NGC 7600 or NGC 3923.
Instead of mergers.
Right. Instead of just being leftover debris from galactic mergers, the idea is that the underlying dark matter halo isn't just a smooth blob. It might be a dynamic dark plasma that's already organized itself into these vast shells. And then gravity makes the ordinary stars follow that pattern.
So the dark matter structure dictates the visible structure. That's a huge idea.
It really is. A cosmic scale application of these plasma principles.
So wrapping that up, dark Earths are expected to have these shells. And what else? Other plasma features?
Yeah, besides the shells, they're also expected to show other typical plasma phenomena. Things like filamentary currents, plasma vortexes, and maybe even plasmoids. These are like self-contained bubbles or blobs of plasma.
This completely redraws the picture of what a planet or a celestial body can even be. Okay, let's talk mapping the unseen. Where is this dark matter, specifically around Earth and the Moon? Is there any observational evidence, even subtle hints?
Well, it's not just pure theory. There are calculations and some intriguing observations. Ewis and Siegel, back in 2008, calculated that the dark matter density within Earth's orbit should be significantly higher than the galactic average, maybe 10,000 times higher, or even more.
So we're definitely sitting in a thicker patch of it. And between the Earth and Moon.
Yeah. Stephen Adler in 2009 did some calculations based on really precise laser ranging data, bouncing lasers off mirrors on the Moon and tracking satellites.
Okay.
He estimated there could be about 24 trillion metric tons of dark matter just floating invisibly between the Earth and the Moon.
24 trillion tons, that's hard to grasp.
It's roughly the mass of all of Earth's oceans combined, just there, invisibly. He even suggested this unseen mass could be responsible for some weird anomalies seen in the orbits of spacecraft doing Earth flybys.
The flyby anomalies, right?
And he identified a region, the Adler Line, about 70,000 kilometers out from Earth's center, where the density of this dark matter cloud seems to peak.
So maybe not just theoretical, there might be actual gravitational effects we're seeing. What about right here on Earth's surface?
Well, more recently, in 2023, Rebecca Lean and colleagues published studies suggesting there could be a really high concentration of neutral dark matter particles right here, essentially floating on Earth's
How
surface.
high?
Their estimates suggest it could exceed the local galactic halo density by 10 to 15 orders of magnitude. That's a 1 followed by 10 to 15 zeros. It's almost unbelievable number,
Right.
suggesting we're constantly swimming in it.
Wow, just constantly immersed. And inside Earth itself, deep down.
Yeah. Also in 2023, results from experiments like IceCube and Super Kamiokande neutrino detectors essentially suggested that dark matter captured by Earth's gravity could potentially make up a significant chunk of our planet's mass.
How significant.
The analysis hinted that maybe up to 20% of Earth's total mass, and possibly around 30% of the core's mass, could actually be accumulated dark matter.
30% of the core. Our planet might be way more porous or mixed than we thought.
It certainly suggests a much more complex picture of Earth's interior.
Okay, so let's try to summarize the overall map or topography of this lowest energy dark Earth-Moon system. How's the matter and charge laid out, roughly?
Okay, starting from Earth's center and moving out, you'd expect the highest density of positively charged dark particles packed into the Earth's core, the E+ region, mainly because the volume is small.
Right.
Then, moving outwards towards the surface, you'd find a medium to high density of neutral dark particles, likely mixed with roughly equal numbers of charged particles. Then, much further out, you hit that big, diffuse spherical shell, dominated by negatively charged dark particles. The E region peaking around that 70,000 kilometer Adler line.
Okay.
And it's important to remember, overall, the whole system's expected to be pretty much quasi-neutral. The total positive and negative charges should roughly balance out.
And how does this pattern extend towards the moon?
It sort of mirrors itself. As you get closer to the moon, you'd find a slight increase in negative charge density in the moon's outer shell, the M region, maybe around 12,000 kilometers from the moon's center.
Okay.
Then, closer to the moon's surface, the neutral particle density would increase. And finally, deep inside the moon's core, you'd find a peak in positive charge density, the M+ region.
And between the Earth's negative shell and the moon's.
In between the E and M regions, the theory suggests there's just a very thin, tenuous, neutral, collisionless dark plasma.
And finally, there was mention of a dark bridge.
Yeah, potentially. When the moon is at perigee, its closest point to Earth, the gravitational pull between the two might be strong enough to draw out a faint temporary dark bridge of plasma connecting the lowest energy dark Earth and dark moon.
It really paints a picture of this incredibly complex, dynamic, invisible system running in parallel to our own.
Exactly. Deeply interconnected.
This has been absolutely fascinating, a real journey into the unseen. So just to recap the main takeaway, dark matter, according to the theory, isn't just some abstract filler out in space.
Right.
It's proposed to form actual structures, dynamic dark Earths and dark moons that are right here interpenetrating our familiar world. We've talked about how plasma physics, these super weak electric and magnetic fields and gravity, could scope these things into nested shells, distinct charge zones. It paints a picture of a universe that's way more layered than we usually think.
Yeah, it really highlights this idea of a deeply interconnected cosmos where the unseen constantly influences the seen, and maybe vice versa too. An invisible counterpart for almost every major celestial body.
So here's a final provocative thought for you, our listener, to mull over. The paper goes even further, suggesting some of these nested shells within the dark Earth could potentially harbor a dark biosphere, one that supports dark plasma life forms. I mean, what would that even mean? If our own planet isn't just home to the life we see, but maybe also hosts an entire ecosystem of unseen dark matter beings, literally flowing through us and around us right now.
It's mind-boggling.
How might exploring these ideas further completely reshape our understanding of what life even is and where else in the universe it might exist? Something to think about.